In February 2023, Meta published a paper on a new family of foundation models. Within weeks, the release catalyzed an entire ecosystem of open-source large language model development that continues to dominate the field. Up to that point, the industry operated under a fairly rigid assumption. To compete with the top-tier foundation models, you needed two things: an incredibly complex novel architecture and a massive, strictly guarded proprietary dataset. Meta abandoned both of those requirements. If you look at the underlying code for LLaMA, you will not find a new architecture. It is built entirely on the standard transformer decoder, the exact same structure introduced back in the original GPT-1. They took that standard decoder and applied exactly 3 specific, heavily documented microarchitectural tweaks: RMSNorm, SwiGLU, and rope. The model's design reflects a specific priority: optimizing for the hardware constraints of the end user. Look at the hardware requirements. GPT-3 requires 175 billion parameters, meaning it demands a massive multi-server cluster just to load the model into memory. LLaMA achieves its results with a highly optimized 13 billion parameter model, built specifically to fit entirely onto a single commercial GPU. Across standard benchmarks, that 13 billion parameter model systematically outperformed the 175 billion parameter GPT-3, despite being roughly 10 times smaller in volume. Unpacking how Meta achieved this is essential. LLaMA provides the precise engineering blueprint for maximizing efficiency, and it does so using nothing but publicly available data. To understand the recipe, we isolate the 3 modifications made to the standard GPT decoder block. First, the normalization node and the feed-forward network. Standard transformers use LayerNorm, which subtracts the mean of the inputs. Meta discarded the mean subtraction entirely, implementing RMSNorm. Empirically, subtracting the mean from the data provides no meaningful benefit to the normalization process. It is mathematically irrelevant. By taking this simplified equation and applying it strictly to the inputs of each sublayer rather than the outputs, they guaranteed higher stability throughout the training cycle. Because RMSNorm only scales by the energy, or the root mean square of the activations, it is noticeably cheaper to compute than standard LayerNorm. Next, they modified the feed-forward network. Instead of a standard ReLU activation function, they implemented a gated linear unit known as SwiGLU. This function calculates 2 separate linear projections of the input. One branch passes through a nonlinear activation, and then it is multiplied element-wise by the other branch. Functionally, one vector acts as a dynamic gate for the other, allowing the model to route information more precisely. This engineering constraint requires a third weight matrix, W3, threatening to expand the layer's total parameter count. To counter this, engineers deliberately shrink the feed-forward matrice's internal dimension, reducing it to 2/3 of its traditional width. By constricting the width while adding the gate, they successfully integrated SwiGLU's advanced routing capabilities without expanding the model's overall parameter footprint. The final architectural change tackles how the model understands the order of words. Standard models use absolute positional embeddings, adding a static coordinate to every token at the input layer, which struggles to generalize to longer sequences. Instead, Meta implemented rotary position embeddings, or rope. Rope physically rotates the query and key vectors in the embedding space based on their position in the sequence. When the attention mechanism calculates the dot product between these vectors, the resulting score relies entirely on their relative offset to one another. While rope itself was an existing technique, Meta deployed it with a specific structural deviation. They implemented these rotational embeddings inside every attention layer throughout the entire depth of the network. RMSNorm for stability, SwiGLU for efficient gating, and per-layer rope for spatial orientation. Those 3 localized adjustments are the only differences between LLaMA and a standard 2018 GPT decoder. With the architecture locked, we have to look at what they fed it. Meta discarded the practice of scraping proprietary, hidden text. They built their corpus using strictly public sources: CommonCrawl, C4, Wikipedia, and Github. They gathered a total of 1.4 trillion tokens. The decision of how long to train a model on that data is traditionally governed by a mathematical standard known as the chinchilla scaling laws. The chinchilla formula states that to get the best possible model for a given compute budget, you should scale the size of the model and the size of the dataset equally. The widely accepted optimal baseline is approximately 20 tokens of data per parameter. Meta ran the math on their compute budget, looked at the chinchilla limit, and deliberately engineered a violation of it. They took their 7 billion parameter model and pushed it relentlessly through nearly the entire 1.4 trillion token dataset. That yields roughly 143 tokens per parameter, scaling data volume 7 times past the recommended ceiling. The training loss curve, the model's error rate, did not plateau. It continued a steady decline well past the 1 trillion token mark. They ignored the optimal ratio because they changed the primary optimization goal. The chinchilla scaling law optimizes strictly for the cost of training. Meta optimized entirely for the cost of inference. By investing massive amounts of compute upfront to overtrain a small network, you construct a system that is drastically cheaper and significantly faster to serve in a live production environment. They applied this same extreme token scaling philosophy to a much larger 65 billion parameter variant. But scaling a model of that physical size introduces severe hardware limitations. The pure math of a 65 billion parameter architecture cannot simply be executed on standard training clusters. The sheer volume of intermediate activations generated during the forward pass will immediately hit an out-of-memory ceiling, halting the GPUs entirely. To bypass this physics problem, Meta engineered causal attention to calculate its scores without permanently storing the masked weights in memory. They combined this with manual backward checkpointing. Instead of keeping every intermediate activation in memory, the system dynamically clears blocks of memory and recomputes those activations on the fly. You drop your memory footprint beneath the ceiling, but pay a penalty in total computing time. To claw back that lost time, they implemented rigorous model and sequence parallelism, carefully overlapping their raw matrix multiplications with the communication latency running across the GPU network. The architecture dictates the capability of the model, but actually putting a 65 billion parameter system through 1.4 trillion tokens relies entirely on this aggressive systems-level memory engineering. When we return to the final benchmarks, the yield of this highly optimized recipe becomes clear. The 13 billion parameter model systematically surpassed the performance of the 175 billion parameter GPT-3, while remaining small enough to serve on a single commercial GPU. At the top end, the 65 billion parameter variant competed directly against massive systems like Palm 540B and Chinchilla 70B, using only its publicly sourced data. Meta's decision to release these model weights directly to the public provided the community with a high-performance foundation. Access to an inference-optimized base model allowed engineers anywhere to begin fine-tuning competitive systems without needing thousands of dedicated GPUs. Evaluating the original LLaMA release does require specific professional caveats. This is strictly a base model. It completely lacks the instruct tuning or reinforcement learning from human feedback required to function as a chat assistant. Empirically, it performs poorly on rigorous mathematical reasoning benchmarks like Minerva, and because it relies entirely on public scrapes, it natively inherits the bias and toxicity of the open web. A standard GPT decoder, 3 localized mathematical tweaks, entirely public data, and a focus on inference scaling, LLaMA laid out the raw engineering blueprint, proving exactly what it takes to build a highly efficient foundation model.